Ladies and gentlemen, welcome to the Geological Society and our third public lecture of 2019. My name's Sarah Day. I'm Head of Media Relations and Outreach here at the Geological Society. And some of you may have noticed that we've designated 2019 our year of carbon. And throughout the year, we've got a series of conferences, lectures, and education resources which will be taking place to highlight that theme, including this talk. So I'm pleased to introduce our speaker, Kiseeva, who will be telling us about diamond windows into the deep earth. Diamonds are composed of crystalline carbon and form at high pressure. They commonly incorporate pieces of surrounding material when they form, and while these spots may not be popular with jewelers, they can provide us with insights into conditions deep in the upper mantle and in the mantle transition zone. Dr. Kiseeva will tell us how these inclusions form and what they can tell us about the composition of the deep mantle. She'll also explore how these insights are helping us to unravel the deep carbon cycle. She obtained her PhD at the Australian National University and worked at the University of Oxford as a postdoctoral researcher and NERC Independent Research Fellow. She recently relocated to the University College Cork, where she's a lecturer. Please join me in welcoming Kate Kiseeva.
Thank you very much, Sarah, and it's a great pleasure and a great honor to be in this audience, and thank you very much again for the invitation. Basically, when I was doing my PhD in Australia, one of the topics I was studying was deep subduction of different carbonates and their relations in and how they behave in the deep mantle. And I very soon became fascinated with another form of carbon, not in the carbonate, but in diamond. And I think throughout my following career, I've been trying to return to that topic and to learn more and to investigate more, and I got really intrigued and fascinated, and I hope that this study will carry on and will continue. And also I hope that by the end of this lecture, I will also convince you that diamonds are incredibly important, interesting, fascinating, and intriguing objects to study. So, but before I go to speak about diamonds, I would like to acknowledge that, as Sarah said, it's a year of carbon. And carbon is undoubtedly one of the most important elements on Earth, in that it's a backbone of molecules and living organisms. And these few words I took, and the same as this picture, I took from the website which is called Deep Carbon Observatory. And a few weeks ago, there was Bob Hazen here giving a talk. So also carbon is, despite our efforts, to decarbonize energy, carbon plays a very important role in our fuel supply and every day-to-day energy supply. Again, if we raise the question of carbon cycle, probably the majority of you will immediately think of the climate change and those global changes that we experience right now with the global warming. But for me, probably, and for a lot of people in geology, carbon cycle sometimes goes a little deeper than just the surface. And looking at this picture, you can probably see that the majority of carbon on this planet is actually in the core. And then there is about 8 to 9% of carbon in the mantle, and only a very small amount of carbon is in the biosphere, atmosphere, and in the surface. So speaking of carbon, and there is a lot of it on this planet, by the way, crust, mantle, and core contain about 99% of carbon. So, but before I continue and talk about diamonds and all the other fascinating things, let us go a little bit about and talk about the structure of the Earth. And we have a crust, which is a very thin layer on top of the surface, then the upper mantle, and these numbers stand for the thickness of each of the layers rather than the depth at which they occur. Transitions, though, a fairly thin layer between the upper mantle and the lower mantle, and we'll probably concentrate a little bit on it today. Then there is a lower mantle, the outer liquid core, and the inner solid core. So how this evolved through time, and it's fascinating to think that even about 70 years ago, or even less, the understanding of how the Earth works and how these layers interact between each other was different to what we know now. So this is a slide of some adapted from a lecture by DiPaolo and Hart. And basically, these researchers pointed out that in 1950s, the idea was that there was a kind of a solid or rigid lid between upper mantle, which was more or less chemically heterogeneous and mineralogically heterogeneous, and the lower mantle and transition zone that was more or less homogeneous, consisting of similar minerals and similar composition. So they also, although acknowledge that there are cratons, or these solid, rigid blocks of lithosphere, which are stable for billions of years, they did acknowledge subduction, although it was not really clear how these layers interact. Now, when we look at the mantle and at the Earth, the picture is much more dynamic. And we can see that there is a constant moving of material, although it's still unclear on which scale and how fast and which age scale as well. We see the subducting slabs coming down, and some of them get stuck in the transition zone, release some fluids, and these fluids later get upwelled and interacted with the overlying mantle. Then we have the other subducting slabs, which probably percolate all the way to the core mantle boundary and give rise to the plumes. So it's all different. And looking at this, we can say that carbon is also probably a part of all of this interaction and movement between the different layers. So, but how do we know, and how do we study the Earth, and how do we actually try to get that picture about the composition and the structure of the Earth? And of course, the most common and the most probably oldest method would be seismology. And it's geophysics. Then the second one is experimental petrology, and ultimately the natural samples. So let me go very quickly through each of these methods. Seismology, and it's been shown that there are two types of waves: primary or compressional waves, which are called P waves, and secondary or shear waves, which basically travel through the Earth at different velocities. And these velocities are correlated with the density of the material which they percolate and go through. So here, for example, if we look at the P wave, we can see that the velocity rises and goes higher and higher up towards from the upper mantle into the transition zone and later into the lower mantle. Then it drops because of the liquid outer core. At the same time, S waves drops completely because it doesn't travel through liquid layer, and then it catches up in the solid outer inner core, and the same here with S waves. And you can see how well these two waves correlate with the density of the material which is present in those regions. Also, you can see this kind of a step function, or a bit of a zigzaggy kind of pattern of the density and velocities. And the biggest changes occur actually in this particular region between the upper mantle, transition zone, and the lower mantle. So this is, of course, correlated with the density, but how do we know what kind of material in terms of composition and the structure of these crystals was at those depths? So, and this was picked up later in 60s and then 70s by experimental petrology. So with the rise of experimental labs in Carnegie Institution in the States, and also in the Australian National University, those were probably the biggest two at the very, let's say, dawn of experimental petrology. People started trying to run experiments that modeled or let's say, they mimicked the PT conditions, pressure and temperature conditions in the deep Earth. And through that, they managed to create some assemblage and to see the minerals which allegedly are situated and occurring in those regions. So let's look a little bit about experimental petrology and see how it works. In particular, I'm of course interested in showing that to you because I am an experimental petrologist, and that was the main part of my PhD and how I operate. So it all starts in the lab with just chemical components. It can be silica, aluminium, calcium, magnesium, all sort of major elements which we find on Earth or in the rocks on the surface. So then we grind them together, mix them well to make it more or less homogeneous, and then we take them to what is called a high-pressure, high-temperature experimental press. This particular press is called a piston cylinder press, in that there is a piston that actually pushes through, generating high pressures, and at the same time, through the electrical current and thermocouple, we can measure the temperature. So we run experiment in one of these, and this particular press can probably generate conditions equivalent to maybe around 100 kilometers depth. There are other experimental presses like multi-anvil press or the diamond anvil cell, which can generate much deeper conditions up to the lower mantle or even the earth core. But this one is kind of my favorite. It creates fairly large assemblage, and don't take me by my word when I say the large assemblage. So now, what do we actually get as an yield from these experiments? And this is an experiment, an experimental result. And this is my palm. And if you look at it, the actual experiment is not the round epoxy ring around it. It's the actual black dot in the middle. And not even the black dot, but something which is inside that black dot, which is a capsule that contains material. So you can probably agree with me that it's fairly small. Almost. So actually, if we look at diamond anvil cell experiments, I won't even probably be able to hold them, or you won't even be able to see them on my palm, how small those are. And these are the crystals severely magnified from this particular little guy. The scale is 20 microns. So 20 microns, if we take 100 microns, it stands for 0.1 millimeter. 20 microns will be 0.02 millimeters, so 200ths of a millimeter. And these are the crystals that allegedly crystallize at about 3.5 GPa, which would make it around 100 kilometers depth. These are the garnet crystals, a little brighter, some coesite, which I can't even see here, this slightly darker one, and a Kleiner Parks crystals. And you would probably look at it and say, how do we analyze those if they're so small? And surprisingly, currently, our methods and our analytical techniques reach the point that we can actually analyze this material. And we can analyze something which probably even 10 times smaller than this. This is an electron microprobe in the University of Oxford, and it can give us the major element composition of these crystals. For the laser ablation that analyzes minor element composition, we probably need slightly larger crystals, or about the size of this garnet, but it's still doable. So, which is great. It means that we can perform these experiments in the lab, and that's what was done predominantly in 1970s and 60s and then 80s. And then we can transfer that and compare the densities that we got from seismics. And this is the major application. We can also study, for instance, and this is only one of the applications, subduction at different levels. For instance, the shallow subduction, then the slightly deeper subduction, and how the assemblage, the composition, and the melts change. So all of this is pretty exciting. Now we don't need to go in the field and collect the samples. We can do it in the lab. And this is one of the phase diagrams that was generated as a part of both natural sample observations and predominantly seismics and experimental petrology. So if we look at this diagram, and I'll walk you really fast through it, this is an upper mantle. The transition zone starts about 410, and we can see the major phase in the upper mantle is olivine. It's a green crystal, which is probably familiar to you, which is called peridot, if we talk about jewelry. Then there is a little bit of garnet, a beautiful red, amazing color, amazing earrings or bracelets. So then we've got Kleiner Parks, another green mineral, and a bit of orthopyroxene, but let's consider them all as pyroxenes. Once we traverse the 410 boundary, or this region, we get into the mantle transition zone, and although the composition of olivine doesn't change, the structure changes, which gives us this step rise in density that you've seen on the previous picture of seismics. So that phase is the same as olivine, but it's called a beta olivine or Wardsleyite. Then if we go a little deeper, it's ringwoodite, again, the same as olivine, but again, a different spinel type structure. So, and at the boundary, bottom boundary of the transition zone, which is at 660, olivine ceases to exist in its form of this Mg Fe2SiO4, and then the phase assembly just changes again into magnesium perovskite, which has currently finally been renamed into the mineral called bridgmanite, ferropericlase, and a bit of calcium perovskite. Simultaneously, the field of Garnet, this red field, rises, and again, it's completely out at the about 660, at around the lower mantle. So you can see that mineralogy changes quite a bit, and that predominantly was found by the experimental petrology, and so does the density in the step change in density throughout the traverse and section of the mantle from our upper mantle to the transition zone into the lower mantle. And it's considered that these phases pretty much exist in the lower mantle in almost the same form throughout the entire depth of the lower mantle. So now the third way of studying samples, we've talked about seismics, about experimental petrology, and now let's see what can actually natural samples tell us. And one thing which always fascinates me here is when I say, how deep can people drill? And when I go and speak even to my students who are the first or second year geology students, they look at me and say, and I always ask them the same question: what is the deepest drill core humanity drilled? And some of them go to something like 150 kilometers and go, oh, good on you, that's really good, because that's not quite the case. So this is as far as we can go in comparison to the entire depth of the planet. So it's not really too competitive in comparison to experimental petrology or seismics. Then on top of our deepest borehole, we have what is called mantle xenolith. And just to tell a little bit about the word xenolith, is a foreign rock. So when we have volcanoes erupted, magmas erupted, then they sometimes bring little bits of mantle and they collect them on their way to the surface. So those rocks foreign to the magmas which erupt are called xenolith. And they come from usually up to 150 kilometers depth. So we kind of enlarged our range of natural samples. And the last one, that again has only started emerging as a new field, a new method of studying the Earth, are the inclusions in diamonds. Because some of them come from up to 700 kilometers, and this is already the lower mantle. This is quite fascinating because inclusions in diamond existed there for decades, but again, they're usually so small that it was pretty impossible to study them. And only recently, maybe about 20, 30 years ago, there was found a great location from where very deep inclusions come. And this is in Brazil, in Juína was the main one of them. So let's talk a little bit about volcanoes. And a typical volcano, probably familiar to everyone here, is in Hawaii. How deep are the magmas coming in Hawaiian volcano? It's absolutely beautiful, amazing eruptions. These are little guys, which I call mantle xenolith. This is basaltic lava and a little bit of mantle, green olivine, which, if it grows larger crystal, would probably be able to be used for jewelry crystals as peridot. And usually the depth of so-called magma chamber underneath Hawaii is something around 80 kilometers, maybe a little high, like 90 or 100 kilometers. And this is considered very deep, because consider that magmas have to rise from 100 kilometers depth in order to erupt in Hawaii. However, this is not the deepest volcano. And the deepest volcano, which can traverse and climb and ascend up from almost 200 to 250 kilometers, are called Kimberlites. So, and these, familiar to you as huge, huge diatreme, huge holes on Earth. And just to give you a bit of a scale, this is a city called Mirny in Siberia. And you can see that the Kimberlite mine is probably twice or three times bigger than the city, which isn't too small. So the diameter of this particular pipe is about 1.2 kilometers. There are other pipes which are just as big. Unfortunately, we can't see these volcanoes erupting today because I think the youngest Kimberlite volcano, although there are kind of different opinions if there are some younger Kimberlites than that, but we can be talking about 30 million years ago. So these volcanoes were more prevalent in, let's say, Jurassic and Mesozoic and maybe a little older than that. But what we see now, we see the leftovers or the cross-sections of them. They look like big carrots and kind of expanding towards the surface. And they have very, very deep channels. And it's considered that they had very explosive eruptions. And they carried a lot of material from the depths of 200 to 250 kilometers deep. So a couple of more beautiful pictures of these Kimberlite mines. You can immediately see the difference between those situated in the northern parts where there is cold and polar sides. This is Diavik Mine in Canada. These two are in Botswana. So both are probably amazingly great place to work on, either at -20 or at +40. So I visited these two, and this is about 1.2, 1.4 kilometers cross section. It has two Kimberlite pipes, two heads of those two carrots, although the channel deeper goes into one single channel. Absolutely amazing rocks, amazing place to be, and although it doesn't have to do with the diamonds and stuff, I will tell you a little bit more about the actual Kimberlites and their mining because I find it absolutely fascinating. So why do we think that they're so deep? And it has to do with this phase diagram that shows you the stability fields of graphite, which is carbon, of lower pressures, and diamond, which is the same element, but at much higher pressures. So in order to have diamond in the rock, you have to be at about at least 120 kilometers depth. And we know that Kimberlites bring diamonds to the surface. So it means that they must come from something in about this area, or they calculated the pressure temperature gradient throughout the mantle, and they saw that it's about this particular triangle of different pressures from where these Kimberlites can originate. So that would be at around 160 or 150 kilometers and about 1300 degrees C. And from there, these Kimberlites can grab some diamonds from the mantle and bring them all the way up to the surface. So back to mining Kimberlites. It's a very interesting rock, and some of the geologists who worked here in Botswana, they told me that they've never seen a diamond in their life. So if you think that these Kimberlites just basically erupt and you go and collect diamonds, that's not quite the case, unfortunately. And the Kimberlites themselves are pretty ugly rocks. So they are not great. They are very crumbly. They are greenish, grayish color. They have some crystals in them, but once you take them into your hands, they're quite porous, and they're not really that great. But they have great inclusions in them and great xenoliths. So what happens next? These huge lorries of probably the size of your house carrying tons and tons of Kimberlite to the factory. And then they go through multiple processes of enrichment and filtering. And diamonds have quite unique qualities. They have fairly high density, they are fluorescent, and they also do not really crush together with the rest of the rock. So through crushing this and going through multiple stages of different filtration and enrichment, they finally get to sorting and evaluation. And there's another huge factory where you can probably only get through 10 or 20 layers of security, and there are people who just sit and tediously collect these diamonds and separate them into different classifications. And these people are also amazing because they can tell a difference between slightly yellow, a little slightly yellow, and even yellowish diamonds. So there are about 20,000 types of a classification of diamonds. So, but okay, let's get back to geology because I'll get too carried on by the diamonds and the beauty of the minerals themselves. So if we get back to Kimberlite pipes, the question is, where are the diamonds inside this pipe? Are they in the Kimberlite, or are they actually brought to the surface by something else, maybe by those mantle xenoliths? And the answer is that we find them in 3 different locations. There are two types of, let's say, major types of xenolith, and unfortunately I have to give you a bit of terminology now, but I promise no more terminology, just an eclogite and a peridotite. So an eclogite is a rock that consists of two minerals. It's garnet, a red mineral, and Kleiner Parks, green mineral. And these rocks are considered products of some partial melting of peridotite. So they are probably primary, but not quite primary. There's something being there that melted to create them. And they can probably be also compared to the ocean floor basalts. So if we have these basalts on the surface on the ocean floor and then we subduct them deep into the mantle, it's very likely that we'll end up with something like an eclogite at about 100 kilometers depth. So, and the second rock is peridotite, which consists of 4 different minerals. Olivine is green. Well, 3 of them are green, so it's not really very informative. But you see also garnets, which are purple minerals, and they are the same garnets as here, but because they contain quite a bit of chrome, the color of this garnet is slightly different. So each of these 2 xenoliths, or bits of the mantle that were carried to the surface, contain and can contain diamonds. On top of that, diamonds can also be found just in situ in that kimberlitic rock itself. So, and here is a bit of a sketch of how kimberlites get to the surface and descend to the surface. We have this big craton, and on Earth there are cratons in Africa, in Australia, Siberia, Brazil, Canada. These are very stable, rigid blocks which are considered not to change their composition much for billions of years, unlike a lot of other slabs which get subducted and again circled and get back through the mantle magmatism. Cratons are stable and they've been there for 3 or even more, up to 4 gigayears. So at the bottom of the craton, it's fairly deep. It can get down to maybe 250, 300 kilometers depth. And at the bottom, there are diamonds, which are, as we've just discussed, deeper than about 120, 150 kilometers. So, and these kimberlite pipes, the red little channels, they travel from somewhere at the bottom of this craton, carrying this material that they capture on their way to the surface. And they travel quite fast. They need to be actually on the surface within hours. Otherwise, the diamonds will potentially melt or disappear. So if we take diamonds themselves, so what do we know about that? What is that basic information? And diamond is just carbon. It's pure carbon, unfortunately, because if we had more impurities, we would be able to study those impurities and their differences, and then we'd be able to say something more, some more information about where they derive, which particular conditions. But here, the only main impurity is nitrogen. We know that diamonds are stable in the deep mantle, and we know that usually they form from fluid or melts. Carbon has 15 isotopes, but there are only 2 that we can use, carbon-12 and carbon-13, because carbon-14 is radioactive, and you probably heard of radiocarbon dating method, which mostly refers to fairly young biological material. And if we study these 2 isotopes, we'll learn something about the provenance and the origin of these diamonds. So this study was done, and quite a lot of it. And there are 3 different reservoirs of carbon isotopes on Earth. One of them, which is called mantle, or what we consider to be a typical mantle, delta carbon-13. So this is just the difference between the heavy 13 isotope of carbon and the lighter 12 isotope of carbon. And this delta carbon-13 in the mantle is about minus 5.5 per milli. This is the way it's usually described. If we take the surface, though, or the crust, or the allegedly subducted oceanic crust, we can find carbon in 2 different ways, in types. It's in carbonate, with the delta carbon-13 being different from the mantle at around 0 per mil, and it's inorganic carbon in sediments, which is very different. It's between minus 20 and minus 40. So if we have a subducted oceanic crust that has a little bit of carbon in it, and it subducts deeper into the mantle, we would assume there to be some kind of middle ground between minus 20, minus 40, and 0, which will be lower, potentially lower than the mantle value. And now let's see what actually carbon isotopes in diamonds tell us. The scientists, and this is a study by Stachel and Harris, took two different types of diamonds, those coming from peridotite, which is allegedly considered a typical mantle rock that is always around in the mantle, and eclogite, the second one that is probably a product of partial melting of peridotite, and that potentially could sometime in the Earth history be located on the surface of the oceans and on the ocean floor. So these rocks potentially didn't see the surface, and these saw the surface, or some of them at least saw the surface. And if we look at the carbon isotopes of the diamonds that come from peridotitic paragenesis of type, we can see that the mean, the concentration is right on the mantle of minus 5.5. While if we actually look at the eclogites, you can see a very big fluctuation or a diversity of different carbon isotope compositions. And this is probably kind of mundane, and we can say, okay, but we knew that eclogite is a partial product of partial melting of peridotite. But at the same time, think about people who were doing these studies in the 1960s and 70s, and they were probably, there were some ideas which opposed to the deep subduction. So back then, it was kind of indicative of the fact that these eclogites were on the surface at some stage in the Earth's history. Then they were subducted all the way into the mantle, got incorporated into the Kimberlite rock or Kimberlite magmatism, and then got back to the surface. So they did the whole circle from being mantle, crust, back mantle, and back to the crust. So that is something we can just see by carbon isotopes. And what else can we look at in the diamonds? And of course, these are the diamond inclusions, and there are quite a few of them. And if we look at them and start studying them, we can probably get some more information. Again, when I get back to this slide, when Kimberlite travel, the sources of Kimberlite are not really limited to this end of the bottom of the craton, but some of these sources come from the, let's say, from the deep subducting slab that releases certain fluids, and from those fluids some diamonds can crystallize. How they get incorporated into these cratonic roots is still a little unclear, but more or less you can say that there is some mantle melts and fluids. They get into the bottom of craton and they get somehow stuck and involved into the Kimberlite magmatism. And the types of different inclusions currently we have, just to give you some overview, there are two general types. The types which come from the upper mantle of this what is called cratonic lithosphere, or these rigid cratonic blocks. And those are called cratonical lithospheric inclusions. So, and there are also deep inclusions. So for lithospheric, and this is 2008, they were documented about 2,800 inclusions. So that's quite a good number. But if we talk about everything which is below 250 kilometers, then it's barely 300 inclusions. So that's all that we had for the range between 250 and 700 kilometers. And that's not too much, but nevertheless, it's still quite interesting, it's still quite enough. It's very mysterious. And what types of inclusions are there? And I'll walk you through a few of them. One of the most typical inclusions in diamonds is called garnet. And on previous picture, you've seen that there are garnets more red, which are in eclogite or in the previous basalt. And there are purple inclusions, which come from peridotitic rocks. So these are the two different types of garnets. And garnet mineral is well familiar to us from different jewelry items. And thinking about the size of these inclusions, again, they look amazingly beautiful and great on these pictures. But if we try to get the size right, I probably kind of severely overestimated this image. And they are barely the size of a pea as the actual diamond. But as for the inclusion, it would be tiny. It would be, again, 0.005 or 0.003 of a millimeter. So they are really, really small, yet very beautiful. And the second type of minerals is Kleiner Parks. a green mineral, some diopside bracelets I could find on the web, although I've never really seen them in a real jewelry store. And the colors also differ from slightly more toxic and green, chromium-rich green to more softer grassy green. Another inclusion is olivine, and although olivine is familiar to be very, very green mineral, and peridot is actually a very beautiful green color, because these inclusions are so small and so thin, you don't really see the color, and olivine is usually very transparent and almost whitish in diamonds. And it's not too common in comparison to garnet and Kleiner Parks, and despite being the most common mineral in the earth mantle. And lastly, one of the most common inclusions is sulfide. Sulfide, or fool's gold, called pyrite, is quite common and very, very common in sediments on the surface. This is a second type of the sulfide common more from mantle rocks. It's called pyrrhotite. And sulfide is kind of black, opaque, metal-looking inclusion, and sometimes we can even see multiple inclusions of sulfides together with garnets in the same diamond. But it's very important to mention that these inclusions are rare. Even though basically we find them, we have to go through many and many and many diamonds until these inclusions are found. And although De Beers and other companies probably try to put them aside and don't want them, they're only about 2% or even less than 2% of all the diamonds that are recovered from diamond pipes. Lastly, the inclusions above were mainly from this area, and they were quite common. But these guys come all the way from the mantle, lower mantle. And this is a ferropericlase inclusion, which is mostly common for the among those that were found. And it's still a little unclear why this mineral is more common than, let's say, bridgmanite, which is considered much more spread and widely populating the lower mantle. So now, what can we actually say, what can we learn from these inclusions? Now I'll try to give you a few applications, which I think are quite fascinating. And one of them is that, first of all, we can actually see the minerals that exist in the deep mantle. Because before we would produce them in the lab, we would produce them experimentally, but then there would be skeptics who come and say, well, one thing what you do in experiments, and of course you can't control the nature. In nature, the system is much more complicated than in the experimental lab. Like, therefore, whatever you produce, we probably do not want to believe it. So first of all, there's been recently, and most of these discoveries have been done in the last, let's say, almost 5 years. So there's been a recent study in 2014, and finally, people were able to find this phase, ringwoodite phase, in a diamond inclusion. Before, we had olivine and ferropericlase and allegedly some magnesium perovskite, which was not really exposed to the surface. But most of these guys, even encapsulated in diamonds, which can actually transport them without changing all the way to the surface. Ringwoodite was incredibly rare, and this was the first finding. Actually, this particular crystal was crystallized in the lab. So as I say myself, don't get too excited. It's quite large as well, 0.2 millimeter. So the actual ringwoodite crystal was somewhere deep inside this particular not amazingly pretty looking diamond. And they found about 1% of water in that ringwoodite, which allowed a lot of scientists to elaborate on the fact that probably mantle transition zone has oceans of water. Yeah, that was a bit curious and amusing to see in scientific publications, because obviously all of this water is bound in the crystal of ringwoodite, and it won't be like rivers of water in the same way as we expected water on Mars. So another very interesting discovery and potential way of studying the mantle was from dating these inclusions. So there was a study by two Stevens, Steve Shirey and Steve Richardson, who took independent mineral fractions of eclogitic diamonds. So they took independently garnet, sulfide inclusions, and Kleiner Parks inclusions, and they dated them. So, and the same way they took periodicitic inclusions. They took some garnet of peridotite and sulfide. And again, some of them were individual grains that were dated, but the others were hand-picked grains from multiple inclusions, because obviously they're so small that sometimes our analytical techniques and dating techniques do not allow to date one single inclusion. So, and then they derived ages for those which have peridotitic or more mantle-like affinity, and those that were on the surface, allegedly eclogitic affinity. And these are some of the results. They also took quite a good representation, because these inclusions came from different pipes worldwide. They came from Africa, from Siberia, Canada, Australia, pretty much everything they could find. And it was a very, very thorough study, very tedious as well. So what they noticed is that peridotitic inclusions give a wide variety of ages, from Mesozoic or fairly recent to something like 3.2, 3.4, even 3.6 billion years, while all the eclogitic inclusions were younger than 3 billion years. So what does it tell us? It tells us that the mantle inclusions were 3.6, while those inclusions that were probably on the top of the crust were much younger, about 500 million years younger. And they hypothesized that probably there was no flux of material between the surface and the mantle until 3 billion years old. And that, again, was a possibility that the plate tectonics, the way we know it now, subduction of the slabs and all this cycle of material that we see through subduction has only started at about 3 billion years. So the first 1.5 billion years of the Earth history probably was a different mechanism rather than subduction. This is still quite controversial, because there are different schools of thoughts, and some people consider, and some scientists, that the subduction occurred immediately with the formation of this planet, and the others think that it all was kick-started much later, at about 3 billion years. But in any way, through tiny grains and diamond inclusions, we can actually discuss this and give its own angle and its own piece of evidence. And lastly, the last application I wanted to tell you about was something that we've been doing and working on in the University of Oxford in collaboration with a few other universities in Germany, France, and Canada. If we look at the mantle and try to study how oxidized the planet is, and we know that if we go down the beach and we see iron or something irony on the beach, it will be of rusty color, which is indicative of the fact that we have 3+ iron or trivalent iron on the surface, which means that there is a very good access of flow of oxygen, and it oxidizes iron to the highest oxidation state on the planet. Then we also know that the Earth core consists of metallic iron, or basically iron with oxidation state 0. And by studying olivine or typical mantle silicates, we can see that something in between is usually around 2+. So this is a very simplified picture, but we have oxidized iron on the surface, and more oxygen access, and goes to more reduced, and down to metallic iron in the core. And that is more or less, that makes sense, and it's all logical. But then there were some theoretical studies and some ideas about the fact that not all of this intermediate iron is actually divalent, or 2+. And some of this breaks into the 3+ garnet that is incorporated into garnet, 3+ iron, and metallic iron that is incorporated into metallic phase. So, which is quite interesting, because we do expect that there is some metal in the transition zone lower mantle that we don't see on the surface. But at the same time, is there any evidence that in this area, on this part of the Earth, we have actual metallic droplets of iron existing? So, and then just a few years ago, in 2016, there was this finding of a metallic inclusion in diamond, which is probably indicative of the fact that if this diamond came from the transition zone lower mantle, then it could basically pick that little crystal or that little piece of metallic iron and bring it to the surface. So obviously it exists at those depths. And another study that shows the other side of this equation. So we have trivalent and garnet, and metallic just sitting as metallic droplets. Another side was done quite recently in our group. And what we did, we analyzed trivalent or ferric iron in the diamond inclusions, which is quite a fascinating study itself. And each of these red circles represent one individual garnet inclusion in diamonds. You can see that we managed to get some of the inclusions from really, really deep Earth, which is about 14, 16 GPa, and these are equivalent to about 400 to 600 kilometers. And we can also see that with increasing depth, the amount of trivalent iron in garnet actually increases, which is a little strange, to be honest, and it's slightly not commensurate with what we'd expect for the deep mantle when we have this conversion, or let's say transition from more oxidized to more reduced assemblages. And all of these guys are hand-picked grains from mantle xenoliths or larger grains found in the upper mantle. So like crystals from bigger rocks, but these again are inclusions in diamonds. So, and last thing I wanted to touch ground. Before I do that, actually, I'll give you a small summary of what I spoke today, and I wanted to just repeat some of this. So we spoke a little bit about the structure of the Earth, how we study the Earth deep layers, about the deepest volcanoes and how they're mined and what types of rocks they bring to the surface. The actual diamonds, they can tell us a story about from their isotopes. Again, diamond inclusions and 3 case studies, one of the plate tectonics and onset of plate tectonics is potentially 3 billion years ago, different types of minerals that we find in the deep mantle. And again, now we start even thinking about different oxidized material and oxidation of those inclusions in diamonds. And before I finish, I just wanted to come to this beautiful story by De Beers that created this big mystery around diamonds. And I found this blog run by this lady, which is quite interesting. Basically, she pointed out that despite the fact that diamonds are quite common, De Beers managed to create this huge mystery of them and diamonds are forever, so everybody should actually spend a lot of money on buying engagement rings and diamonds. So just to tell to De Beers that carbon is about 4 times more abundant on Earth than copper, and 15,000 more times than silver, 120,000 times more abundant than gold, and I'm not talking of platinum. So De Beers played it so well, they even called it a slogan of the century. This guy, a diamond is forever. And of course, yes, but diamond is a common mineral on Earth. And this, of course, it's very beautiful, it's very nice, but it's not that rare. So another beautiful slogan, the girl's best friends. And I wanted to slightly rephrase it and to say diamond inclusions are much more rare than diamonds. So how about that? Okay, thank you very much for your attention.
Thank you very much for a really fascinating talk. It's amazing how much you can get from these tiny little samples.
Thank you.
We do have a little bit of time for questions. So if you do have a question, can I just ask that you raise your hand, and if you could just wait for the microphone to reach you, and that's so that we can pick up the question in our recording as well. So I think there's one to start with down here.
Thank you. Are you able to say something more about the plus and minus 3 billion years ago, why the plate tectonics was not detected or had not occurred? And was it a temperature effect with the cooling of the Earth or not?
To be honest, it's very hard for me to tell why exactly it occurred that time, but it could be that basically, as you say, that the temperatures were much higher, and basically it didn't have time to stabilize the crust to these big craters. That could be one of the reasons. But what we actually see, and in comparison to the diamonds are just a very small story of those plate tectonics. First of all, there is a lot of modeling done by I think especially Zurich group. And they, through modeling and through computer simulations, they could show that the speed and the amount of volcanism and the temperatures would actually trigger the destabilization of the crust. And then there was another thing done actually by fellow of Royal Society and very famous prominent researcher John Dewey, who studied phase relationship and old cratons. So he looked at the rocks in the field and said, there is no way, we don't see any evidence of plate tectonics in the rocks which are older than about 3 billion years. But then we have other people, also very prominent, eminent researchers like Nick Arndt, who think that it should be 4 billion years old. So it's still ongoing debate.
All right, thank you. Yes, it's not known yet, so that's...
Yeah, it's not known yet. No, I agree with you.
There's one with the microphone already. Yeah.
Hello. Excellent lecture. Thanks very much. One thing I missed, though, was how do the diamonds form? You know, why are they so generally so small, and how do the inclusions get into those small diamonds?
Oh, I wish I was there, you know, like 2 billion years ago. So, no, it's considered, and again, there are quite a few schools of thought, how exactly the diamond forms. So one of the ideas is they are metasymmetric, or let's say they crystallize from fluid or melt. And surprisingly, I even managed to reproduce it in an experiment. So I had, in one of my experiments in the lab, a pool of melt, and inside was a beautiful sitting diamond. So let's consider that that pool of melt also has a little bit of material from outside that just chipped or broke and remained in this pool. Then it could actually incorporate those bits of minerals. So that would be one option. Another, there is a school of metasymmetric people who think that there are percolating fluids. So let's say we have a subducted oceanic crust that somehow some of this carbon and carbonate survived. Once it gets to consider 500 kilometers or maybe shallower depth, it starts releasing fluids and starts melting. So if it melted, these carbonatic melts containing quite a lot of carbon would percolate through the overlying mantle and enrich the rock or metasomatize it. And then little by little, all of these metasymmetric processes will trigger another process, and eventually there will be droplets of melts. And possibly diamond forms from those as well. So that's called metasymmetrically triggered or crystallized from the metasymmetric fluids. And how exactly the diamond inclusion get incorporated, there are two types. Some of them are syngenetic, or those that consider to be simultaneous in their age with diamond. Those are not very, very typical. There are older inclusions, and usually diamonds are actually much younger than the actual inclusions that are in diamonds, and those are called protogenetic. So when they pick little minerals from around.
Okay, thank you.
Yes, thank you for a very interesting talk. The advent of plate tectonics and the subduction that takes place must have been the start of the evolution of the interior of the Earth. Does that explain how there's a variation in the depth of diamonds being formed? I think you said the temperature has got to be 1300 degrees.
Well, I say temperature that we detect on the mantle xenoliths using geobarometers. So there is a range of temperatures between 900 and probably 1300 on those mantle xenoliths that we find. And in order to do that, we need at least usually two minerals in one rock. So we can see the relationship between different minor elements, like, for instance, sodium or magnesium or iron or major elements, and then we can calculate PT, and that's the entire study called geobarometry or geothermometry.
But the production of diamonds is a combination of pressure and temperature, isn't it?
Yes, the formation of actual diamonds, the stability field of diamonds is certainly related to the pressure temperature, as on the diagram. I won't go all the way to the...
No, my question therefore is, with all this activity and its constant evolution within the interior of the Earth, is there an indication that the temperature of the Earth is changing? Has there been any research to...
like one of the previous questions, basically there was a clear indication that in the Archean, the Earth was much hotter. And indeed, the Earth cools down. So although, for instance, now we do not have melts coming to that incredibly high degree melting as it was back in the Archean.
But does the tectonic activity, is that increasing the temperature from that point?
It's hard to tell. I see your question, but it's very hard to tell. I think if, for instance, you compare Earth with smaller planets like the Moon, so on the Moon we do not have any tectonic activity because it cooled down much faster. I don't think Earth is right now at any threat of actually losing the tectonic activity because there is still quite a lot of heat on the planet.
Well, it just, it's another aspect of climate change, I think. If the Earth is warming up from inside, is that
Oh, it's not warming up. If anything, it's just cooling.
Right.
Yeah, it's not
definite,
warming up
isn't it?
from inside. Yeah, no. It wouldn't,
Okay.
because the actual temperatures of the Earth have to do with their size and have to do predominantly with the radioactive decay. So the amount of elements that decayed at the very beginning of the Earth were clearly more than we have now because of the 4.5 billion years history.
Thank you.
Following on from that point about the isotopic ratio, you mentioned that carbon consists of a number of isotopes.
Yes.
And what information can you get from the ratio of those isotopes about the timing and formation of the crystal?
Well, the thing is with the carbon, unfortunately, you cannot really date diamonds with carbon because the radiocarbon method and the decay constant of carbon is very, very short. I can't tell you from the top of my head, but it's a few cells. Yeah. Yes, so you see, you know better. So, but therefore, those elements which are dated by samarium, neodymium, and rhenium, osmium, are dated the actual inclusions in diamonds, because dating diamonds would be quite a futile exercise, unfortunately. So I don't know any studies that dated diamonds themselves, but the inclusions in diamonds, yeah, we can have samarium, neodymium on garnet and Kleiner Parks, and rhenium, osmium on sulfides. And luckily, rhenium, osmium can be done on individual grains, while samarium, neodymium is only applicable to a larger number of grains. So those ages would be model ages. Well, actually, sulfides as well are model ages. And I would say that they're probably not incredibly precise to be very optimistic. So, but nevertheless, we have to work with what we have. And in terms of diamond inclusions, we only have 300 of them, of the deep inclusions. And even if we can date at least 2 of them, it would be amazing.
Have you looked at any inclusions in meteoritic diamonds?
I personally didn't, and it's.
Has anyone looked at them?
I think it would be actually a very, very interesting study. I never had a chance. I think that generally looking at inclusions is not that simple because it's, first of all, there is a very, very big resistance from large companies to share these inclusions in diamonds in the first place. And also there is there is another thing that there is usually a head geologist or a chief geologist in each of the working for the De Beers or Siberian companies or Alrosa in Russia. So, and it's difficult. It's difficult to find the right samples. It's difficult to find them and to actually get access to them. And it's also like in terms of any additional studies, we just didn't have enough methodology up until probably some recent time in the last decades.
And you have to give them back afterwards, do you?
I do, of course. Question? Yeah.
Thank you. It's actually moving on from that last point. How much physical damage to the diamond does analysing the inclusion cause? And could there therefore be a difference between the ones you're allowed to play with and the ones that De Beers are flogging just down the road because they're higher standard?
So there are different methods. There are some methods, and they are only kind of emerging now when you can analyze the inclusion. Depends what you're analyzing for. If you want to do ages, then you probably have to certainly recover it from the diamond and completely destroy the diamond. So speaking about this single inclusion, and I actually will go back, it's actually quite a fascinating thing that when the guys tried to get it out of this diamond, it popped out and completely exploded. So, so this ring without inclusion, the only one that was found on Earth, is not existing anymore. But there are the inclusions, and actually the majority of them, once you decapsulate them from the diamond, they sometimes are lost. Not all of them, though. So the ones I studied, and these were my study, of the inclusions of majoritic or very deep garnets from almost the mantle transition zone. For them, the diamonds were extracted, and then they were polished to expose the inclusion. And once the inclusion is exposed, they could be studied for various methods, including their isotopes. There was done some oxygen isotopes of them. The overlying diamond was done some carbon isotopes of them, and then finally we did ferric ratios and oxidation states. So these particular guys that come from the mantle transition zone were studied as much as we could at the moment. But of course, there are the others that are probably really, really difficult, especially if you have multiple inclusions. You don't want to break the diamond, and also some people do like CT scans and tomography to see their relationship between themselves in the same. Yeah, CT scan is very common for diamond inclusions as well, not just for medicine.
Okay, we should probably call it time there, because you've got to do this all again in a couple of hours. Thank you all very much for coming, and please join me in thanking again Dr. Kate Kiseeva. I promised Gary to put it here. We leave that there? Yep. Okay. I've been told to leave it alone. Okay, thanks. He'll probably come and... Oh yeah, he looks happy. Okay.